Welcome, students, to today's intellectual exploration of a fascinating algorithmic challenge, LeetCode Problem 11, commonly known as the container with most water. In this problem, we are tasked with determining the maximum area of water that can be contained between two vertical lines, represented by an array of integers. Each integer signifies the height of a line, while the width between any two lines is dictated by their position within the array. Our objective is to compute the maximum area that can be formed by any two lines, taking into account both their heights and the distance that separates them. To illustrate, consider the input array, 1, 8, 6, 2, 5, 4, 8, 3, 7. The output which we seek is 49. This maximum area is achieved between the lines at indices 1 and 8, where the height of 7 and a width of 7 yield an area calculated as the product of these dimensions. Join me as we delve deeper into this captivating problem and unveil the strategies to solve it efficiently. The two pointers technique is an effective algorithmic strategy that simplifies solving computational problems by using two variables to traverse through an array or list. Imagine you have a long road with two cars starting at opposite ends. One car represents the first pointer, and the other represents the second pointer. By placing one pointer at the start and the other at the end, you can efficiently examine the relationships between the elements they point to. This technique is particularly useful for problems involving pairs of elements or sorted arrays. For instance, if you need to find two numbers that add up to a specific target, you can adjust the pointers based on their current sum. If the sum is too low, move the left pointer to increase it. If it's too high, move the right pointer to decrease it. This method reduces the time complexity from quadratic to linear, allowing you to explore all potential combinations without unnecessary nested loops. Overall, the two pointers technique is versatile and powerful, helping streamline various computational challenges effectively. Let's dive into the two pointers technique using the problem of finding pairs with a given sum. First, we start by sorting the array. This is crucial because it allows us to use the two pointers effectively. Once the array is sorted, we initialize two pointers, one at the beginning, called left, and one at the end, called right. Next, we enter a loop that runs until the two pointers meet. Within this loop, we calculate the sum of the elements at both pointers. If this sum matches our target, we've found a valid pair, so we store it and move both pointers inward. If the sum is less than the target, we move the left pointer to the right to increase the sum. Conversely, if the sum is greater, we move the right pointer to the left to decrease the sum. This approach efficiently narrows down the possibilities, ultimately allowing us to find all pairs that meet the target sum. By the end, we return the list of pairs we've discovered, showcasing the power of the two pointers technique in a clear and structured way. Optimal space complexity is all about using memory wisely when designing algorithms and data structures. Imagine your computer's memory as a limited shelf space. An algorithm achieves optimal space complexity when it uses the least amount of this shelf space while still doing its job effectively. This is especially important in scenarios with large data sets or systems that don't have much memory available. If an algorithm consumes too much memory, it can slow down performance, increase costs, or even crash the system when it runs out of memory. To achieve optimal space complexity, developers analyze how much memory their algorithms use and make smart choices about how to store and represent data. For instance, they might use data structures that avoid duplicate information or design in-place algorithms that modify existing data without needing extra space. By focusing on these strategies, programmers can create more efficient and scalable applications, which is critical in areas like data analysis or real-time processing. In this slide, we have a function called double elements, which takes an input list and returns a new list where each element has been doubled. Let's break it down step by step. First, we initialize an empty list named result. Think of this as a clean slate where we'll store our new values. Next, we loop through each element in the input list. For each one, we multiply it by 2, which is like taking a single item and doubling its size, just like if you had one cookie and wanted 2. After we double the element, we append it to our result list. Finally, once we've processed all elements, we return the new list filled with these doubled values. This approach efficiently uses space because we only create a new list based on the size of the input list. It's a great example of achieving optimal space complexity while performing a simple transformation. Linear time complexity, denoted as ON, describes a scenario in which the time an algorithm takes increases directly with the size of the input dataset. Think of it like filling a bucket with water. If you double the size of the bucket, it takes roughly double the time to fill it. Here, N represents the number of elements being processed, and each element contributes equally to the total time needed. Understanding linear time complexity is vital, especially when dealing with large datasets. This complexity is common in algorithms where each element must be examined once, like searching through an array or summing its contents. While linear time is efficient, keep in mind that faster options exist, such as logarithmic or constant time complexities. In practical terms, when an algorithm processes each element with a set amount of work, like summing an array, it traverses that array just once. This leads to a runtime that grows in a linear fashion. Grasping this concept is essential for analyzing and comparing algorithm efficiency in computer science. In this example, we have a function called double elements that takes an input list and doubles each of its elements. First, we initialize an empty list named result, where we will store our doubled numbers. This is like preparing a container before filling it with items. Next, we move into a loop that goes through each number in the input list. For every single number, we multiply it by 2, and then add this new value to our result list. Think of this as taking each item out of a box, doubling it, and putting it into a new box. Finally, we return the result list, which now contains all the numbers from the original list, but each one is doubled. This process is an excellent example of linear time complexity, denoted as ON, because the time it takes to complete the task grows in direct proportion to the size of the input list. More numbers mean more calculations, but each one is handled independently and in sequence. LeetCode problem 11 focuses on finding the maximum area of water that can be contained between two vertical lines on a 1D plane. First, visualize an array of integers. Each integer represents the height of a vertical line. The goal is to select two lines that, along with the x-axis, form a container holding the most water. We'll use a two-pointer technique to solve this efficiently. Start by initializing 2 pointers, one at the start of the array and the other at the end. As long as the left pointer is less than the right, calculate the area formed by these two lines using the formula. Area equals the width between the pointers times the shorter line's height. Keep track of the maximum area found. Then, to potentially find a taller line, move the pointer pointing to the shorter line inward. This approach allows us to check all possible pairs while maintaining an ON time complexity, making it far more efficient than a brute force ON scored method. Finally, return the maximum area after the pointers converge. In this problem, we are tasked with identifying two vertical lines from an array of integers that represent their heights on a Cartesian plane. These lines, together with the x-axis, create a container capable of holding water. Our objective is to determine the maximum volume of water that can be contained. Notably, the number of lines, denoted as n, ranges from 2 to 100,000, while each line's height, h, can vary from 0 to 10,000. These constraints are critical in shaping our solution approach. The Python code on the slide addresses LeetCode problem 11, which asks us to find the maximum area of water that can be contained between two vertical lines on a two-dimensional plane. To tackle this efficiently, we use the two-pointer technique, a smart approach in algorithm design that helps minimize time complexity. We start by initializing 2 pointers, left and right, that point to the beginning and end of the list named height. This list represents the heights of our vertical lines. We also create a variable called max water to keep track of the largest area we've found as we explore the container options. The main part of our algorithm is a while loop that runs as long as left is less than right. Inside this loop, we calculate the width of the container as right minus left. To find the effective height, we take the shorter of the two lines using min height left, height right. This is important because the area is limited by the shorter line. Next, we calculate the area for our current setup and compare it to max water, updating it if we find a larger area. To make our search more efficient, we use a greedy strategy by adjusting the pointers based on the heights. If the line at left is shorter, we move the left pointer right to try and find a taller line that could yield a bigger area. Conversely, if height right is shorter, we move the right pointer left. This method ensures we explore the best potential containers effectively, leading to an overall time complexity of ON, where n is the number of elements in height. This algorithm balances clarity with efficiency, providing an elegant solution to our problem. The time complexity of the container with most water problem is ON. This means that the algorithm processes each element of the input array in a linear manner. We achieve this by using a two-pointer approach. Imagine two friends standing at opposite ends of a line of cups. Each friend represents a pointer, and they move towards each other until they meet in the middle. In the worst-case scenario, both pointers will traverse the entire array, resulting in a time complexity proportional to the number of elements, n. Now let's discuss space complexity, which is O1. This indicates that the algorithm requires a constant amount of extra space. Here, we only need a few variables to keep track of the current indices and the maximum area we find. No matter how large the input array grows, the space we use remains the same. This efficiency is crucial, especially when handling large datasets. Understanding these complexities helps us appreciate the algorithm's effectiveness and efficiency in solving the problem.